Okay, so now we're ready for the next step. We know that the LM35 can output a usable voltage. Now what we need to do is actually have a microcontroller that can read that voltage in and do something with it. It's going to be controlling the fans. So now we have to choose a microcontroller to do all that. Okay, so I've jotted down some of our requirements. First thing is the most important pin. We need to receive our voltage in from our LM35, our temperature sensor. Then next we need a output for pulse width modulation of our fan. A third output for the LED pulse width modulated output. Now these two could actually be driven off the same pin. I'm going to drive them separately so that I can actually have independent control of the LEDs, so maybe I can do a startup sequence so you can see that it's actually booting up and operational. And then the fourth line we're going to have is a serial output. Now this one is also optional, but it's nice to have something that you can actually use for debugging purposes, just to make sure that the chip is actually doing what you expect. And so this is basically 4 lines. Now again, it could actually be as small as 2. And for that purpose, this is the chip we're going to be using. So this chip here is a PIC 12F675. It's a 8-pin microcontroller, and 6 of the pins, 2 of the pins are power, 6 of the pins are actually usable for inputs and outputs. So even after using the extra sort of 2 that we don't really need, we're still going to have 2 free pins on this thing. Okay, so next thing, before we even start the programming, we have to sort of do some conversions here. This PIC 12F675 has ADD converters on it, analog to digital converters, and they're 10-bit analog to digital converters. So 10 bits of information gives us a number between 0 and 1023. Okay, so what we have to do is determine how much each of these increments, 0 to 1, 2 to 3, for example, actually means in the end as a temperature. So that range is actually 0 volts to 5 volts. So if we take 5 volts and divide it by 1024, that means that every increment is actually 0.004883 volts per increment. So what's going to happen to get an actual temperature out of this, I'm going to be taking the digital value, so the analog comes in as a voltage between 0 and 5, and we get a number that's usable in the microcontroller, which is a number between 0 and 1023. And I'm going to take that number, and to get the actual degrees Celsius, all I'm going to do is multiply it by approximately this number here, which is, let's call that 49. And then I'm going to divide it by 100. Now, it might look kind of odd. Why am I doing this? It's because this little device uses integer math. Okay, so this is the circuit now with the introduction of the microcontroller. Microcontroller sitting here. Pin 1 is at the bottom left. And with this microcontroller, pin 1 is 5 volts. So we actually have 5 volts coming in on this rail here, this bottom rail. So this is being picked up over to pin 1. And this top rail, this white wire here, comes over with the negative. And pin 8 on this microcontroller, it's 1 through 4 and then 5 through 8. So pin 8, which is the top left corner, is getting ground right here, negative. And what else do we have happening here? We have a voltage probe. So one line of the voltage probe is going over to ground, and the other side is going over to pin number 3 of our microcontroller. And pin number 3 is also going over to our temperature sensor. These leads are just extending over to our temperature sensor, which is just actually taped onto this cup here. And I'm using a metal cup this time to hopefully get a much better heat transfer. And the last thing we have in this circuit is 2 lines going over to this connector here, which is just a serial port connector, which is going over to a computer. So the RS-232 line is grounded, and this is serial data on pin 7 going out to our serial connector. Okay, so the circuit's powered up, and what I have running on there is a very simple program. All it's doing is it's sampling pin 3 here, the analog value, and it's doing that calculation that we spoke about. It's multiplying that whatever's coming in here by 49 and dividing it by 100. And I actually have it being displayed on the screen here. If I tip this up, you can see there's two things. There's this meter here is showing the actual value, the voltage, as we showed before. So this is 0.226 volts, so that averages up to 23 volts. And this is the raw data. So we have the raw temperature data, so the analog to digital value, this is the digital value, is 47 or 48. We can see it sort of fluctuating. And the calculated temperature based on that formula is 23 degrees Celsius. So that looks wonderful. Okay, and I'm just going to try our temperature range again here. This time I'm going to use a syringe so I don't spill everything, and I'm using an icy cup, which is a cup with a bit of ice in it with some nice cold water. It's been sitting in there for about 5 minutes, and I stuck this hot water in the microwave, so it should be nice and hot. And we have the metal cup, which should give us some really good heat transfer. Okay, so I'll put maybe about a fifth of that full of cold water. The temperature sensor is at the bottom rim of that, so it should cool down quite rapidly. Let's take a look at what the meter is showing. Of course, my meter went to sleep. Okay, so that's cooling down quite well. It's showing a count of about 32 and a temperature of 15 degrees Celsius. And we're still slowly cooling down, but that's it's going quite slow now, so I think that's about our temperature. I'm going to introduce some of the hot water. Okay, so syringe full of hot water going into the cup. Okay, so the cup is pretty much full of hot water now. And there we go, we can see our temperature rising quite nicely. Just to get a higher temperature, I'm actually going to dump this fluid out. And fill it only with hot water. Okay, what do we got now? So 48 degrees and climbing, and it looks quite nice and linear. 49 degrees on our calculated temperature, 49 degrees here. We just hopped up to 50. So the range looks good. Our calculations look correct. So I think we can move on to the next step. For more information, please go to alanparekh.com.